I'm Yeonwoo at the Construction Innovation Lab, Seoul National University in South Korea. Today I will present our work title, Database Development and Repair Cost Prediction based on Infrastructure Maintenance Records. Let me start with the research background. In recent years, South Korea has experienced serious infrastructure failures, such as the Jeongja Bridge collapse in April 2023 and the Doring Overpass collapse in January 2023. These incidents highlight the growing risk associated with aging infrastructure. As shown in the chart, the proportion of infrastructure over 30 years old and increasing across all facility types. Notably, the table on the right shows that 76% of bridges rated grade D are over 3 years old, indicate the high risk of failure. Therefore, urgent repair is required due to the sharp increase in aging infrastructure with low safety rating. As infrastructure continues to age, it is essential to understand how many facilities can be repaired within a limited budget and how much each repair will cost. However, in Korea, facilities are managed separately by different authorities and related records that are fragmented. As a result, the FMS lacks a comprehensive repair cost database, making current budget estimation rough and unreliable. To address these challenges, our research proposed three main objectives. First, we aim to establish a structured database dedicated to repair cost analysis. Second, we develop a unit cost estimation model using actual maintenance records. Finally, we aim to support accurate estimation of repair cost. Ultimately, by improving the estimation of maintenance and repair costs, we can ensure the efficient allocation of limited public budget and contribute to the safe and sustainable management of social infrastructure. This slide shows the overall research framework. First, we define a facility breakdown structure based on Korea Special Act. Next, we build a database using repair records and inspection reports, linking cost and condition data. Then we develop a unit cost estimation model using XGboost algorithm. The model predicts cost based on facility characteristics. This approach supports more accurate and scalable cost estimation for infrastructure maintenance. Now let me explain the first step of our research framework. The establishment of a facility breakdown structure to standardize data collection. In South Korea, the Special Act on the Safety and Maintenance of Facility classifies public infrastructure into 15 types, such as bridge, tunnels, dam, ports, and more. We select target facility types from this legal classification and examine their inspection and repair obligations. Next, we define data collection criteria based on this route. At the bottom of the slide, you can see an example of our breakdown structure. We structured the data hierarchical, starting from facility type, then category, structure type, major element, detail element, elemental type, and finally the type of defect. This breakdown system ensures the data is collected in a consistent, detailed, and comparable format. Now let's move on to step 2, the development of a database using real maintenance records. To build a robust and realistic repair cost database, we first collected actual maintenance performance reports from various facility management entities in Korea, including Seoul Facility Corporation, Korea Railroad Corporation, the Express Corporation, and others. These reports, which include both inspection and repair data at the facility or elemental level, were carefully reviewed. From them, We extracted information such as defect types, repair location, and cost details, and organized everything into a structured and integrated database. This is an example of how we built the database. We extracted general information from maintenance records using sources such as the facility management system and repair history data. The extracted data includes facility type, facility name, type of work, project cost, and construction period. We also extracted detailed information from completion reports. This includes repair method, quantities, unit cost, and total cost, such as material level and equipment. By standardizing this data, we built a cost database that reflects actual maintenance practice. This table summarizes the inspection and repair data collected by facility type. In particular, bridges and tunnels had relatively abundant data, so our analysis focused on these facility types. Now, let me explain step 3, the development of unit cost estimation model for bridges. To build an accurate prediction model, we used the XGboost algorithm. The model utilized 3 types of data: bridge specification information, detailed elemental level data, and actual repair records. Since repair costs vary by year, we first adjusted all cost data to present value using the National Construction Cost Index. Next, we performed data preprocessing, which included removing outliers based on the IQR and filtering out categories with low data frequency. As a result, we secured over 72,000 valid data points for training for model. In addition, repair unit costs were classified into 5 ranges by method, such as a sectional repair, surface repair, and injection repair to enhance the interpretability and accuracy of the model. Finally, we trained the XGboost model and evaluated its performance. In this slide, I will explain how we categorize repair unit costs and evaluate model performance using 2 different classification methods. We compare 2 approaches, equal interval and equal frequency. The equal interval method divides the overall cost range into evenly spaced intervals, while the equal frequency method ensures each group has the same number of the data points. As the results show, the equal interval method performed better, achieving 87% validation accuracy and lower MAE of about 53,001. Based on this result, we proceed with the equal interval method for the rest of our analysis. In this step, we explored how the number of cost interval affects model performance. We tested 3, 5, and 7 bins and found that models using 5 bin achieved the best overall accuracy for both surface repair and asphalt overlay method. As a result, we selected 5 intervals as a final binding strategy for cost classification. Additionally, we compared 5 classification algorithms to predict cost range. XGboost showed the best performance across all metrics with accuracy of 91% and strong precision and recall, confirming it as the most suitable model for our task. To ensure accurate unit cost estimation, we use 30 facility level variables, 3 repair-related variables, and detailed elemental level information as input features for model training. The variables used are listed in this table. Next are the experimental results. As an example, we developed a unit cost estimation model for surface repairs of deck elements. Using a total of 7,252 data in tiers, the unit costs were divided into 5 ranges and representative value were assigned to each range. Based on this categorization, the model was trained and achieved a range classification accuracy of 93% with a MAP of 11%. As shown in the confusion matrix on the right, most of the prediction closely matched the actual cost range. This slide presents the overall experimental result of the unit cost estimation models developed for various bridge elements and repair methods. A total of 30 models were developed which tailored to specific combination of structural elements and repair techniques. This slide presents the result of applying the same modeling approach to tunnels. Conclusion of our study. Through this research, we made 3 key contributions. First, we enable integrated managing by constructing a unified repair cost database. Second, we developed AI-based model to estimate repair cost. And third, we support more efficient cost estimation within limited budget constraints. For future work, we plan to expand the infrastructure database with more diverse data, improve model performance by incorporating additional variables such as project scale and work duration, enhance prediction accuracy by developing optimized models for each structure component. This is reference. Thank you for listening.